So welcome to this final lecture in our crash course in probability theory, and for that matter, the entire course of method theory. So this lecture, I'm looking forward to it. It's going to be a bit like, the end of the Lord of the Rings when Frodo and Sam are sitting on Mount Doom and they realize that all their effort, all their struggle, actually converge in singular important moment. And the proof we're going to do today is a strong law of large numbers. It's a bit like that, just a firework of abstract beauty. Okay. Yeah. So you wonder why I have so much hair in my scalp? Because it's a substance called minoxidil, which I've heard what it goes, but it works. Works great. So this is my tip for all the important mathematicians out there. If you want to, hide your nerdy truth cells in a fountain of curly undulating hair by minoxidil and spray every morning. Okay. So if we have a bunch of random variables, x1, x2, etc., how can we figure out whether they converge to something or not? Let's take the number A for completeness. Okay, we interpret that xn goes to A as n goes to infinity. Well, we have this more intuitive idea of what is a random variable, something like going up on the real line with a certain probability. Then clearly, we want to somehow say that the probability that xn is near A increases as n goes to infinity. But in this course, we have learned that random variable is not a random variable that just pops up with some randomness. Rather, it is a function. Down here we have some space omega. Here we have the real line. And a random variable is a function. So the randomness comes from pulling some random omega down here, and then the value xn here is actually the valuation of our xn at that omega. So now, random variable is actually the function. Okay, and with this, now we can easily interpret what it means to be close to A, because then we just think of A as a constant function, and all of a sudden, we have a number of definitions already in place from chapter 2, stating in very traditional theoretic terms whether the sequence of function xn converges to the constant function or not, right? So, interpretation 1. You can hear me. Interpretation 1 would be that the probability of xn minus epsilon be less than, xn minus A be less than epsilon goes to 1 as n goes to infinity, which means, so if we think about it, I mean, there are two ways of thinking about it. So if we think about it here, then, there's some of this probability measure that xn gives rise to that tells you what's the probability of xn appearing in a certain interval here, A plus epsilon, A minus epsilon, right? So like that, we can say that this is actually let me write it maybe as an integral, so limit, and goes to, well, let's keep the limit. Let's just think about what this is. So this would then be the integral of the characteristic function of the variable x, the normal variable, right? The independent variable, x minus a, being less than epsilon. So I'm taking the characteristic function of the set here, and I'm integrating that against what? Against the probability measure that xn gives rise to. So here, xn really just shows up here, generating this measure. A different way of looking at it, if we go to the left-hand side of probability theory, then this is the integral. Sorry, it's not the integral. This is just the measure of the sets of omega such that xn at those omega is within plus minus epsilon of a here. And when we write it like this, we realize that this is just, sorry, of course, the stupid computer crashed. Bullshit. Anyways, what I was saying was, I don't know why I wrote this as an integral. We can write this as a set as well. So this is dxn of that set. But if we look at it here on the so-called left-hand side of things, right? We can consider this as the one fixed measure mu as opposed to one that's this changes with n, right? Here we see that mu applied to the set of omega, so the xn of omega minus a is less than epsilon. If you look at the set here of omega, so this is closed. And like this, we realize that this is nothing but what we know from chapter 3, convergence in measure. But in probability theory, they call it convergence in probability. Which, of course, it's a natural term given this explanation here. Okay, but so now the second way of saying that the sequence of random variables somehow converge to A would be to write limit as n goes to infinity of xn is equal to A almost, well, almost everywhere, but they write almost surely because, well, it's probability, so this means almost everywhere. Now, what does that mean? Again, if we're over here, okay, of course, now if I have a number of random variables, so x1, x2, as we've been discussing, I can think of this as just a r to the power of n, and then they live here and have some sort of probability measure, px1 cross product, px2 cross product, cross pxn, that tells me the probability of x1, x2, the multiple showing up in a certain region here in my multidimensional space. But there's no way to interpret this thing here unless, I mean, here, so for this statement, we could work on both sides. We could understand like this and like this. Here we cannot. Because what does this mean? I mean, as we've been discussing many times, there's no way, or at least there's no easy way of taking the infinite product here, right? So what does this really mean? It requires some thought. However, if we're here, we realize that, these are just many different functions. And then, so we have this probability space down here, omega, which usually can be realized as the interval between 0 and 1, we just learned in the previous lectures. Then for a given omega, that's like the outcome of all the experiments from 1 to infinity. And the value of that outcome is given by xn, the function at that omega, right? So then, this here just means, okay, so this is a parenthesis, I guess. So it means that the set of omega where the function values do not converge to A is 0, or if you want, when it converges to A, the measure of that is equal to 1. Okay, so in this lecture, we're going to look at the proof of I mean, so this is something that can hold or cannot hold. So what we're going to do next is to look at averaging random, the sequence of independent random variables, and then show that this converges to the expectation, the average, as n goes to infinity. Now, then this is called the weak law of large numbers. I mean, the statement I just said is called the law of large numbers. And then if you, the incarnation like this is the weak law of large numbers, and this incarnation is the strong law of large numbers. We're going to do both proofs to, to appreciate the beauty of what we have built here, to see, so the first proof is simple, the second one is difficult, and both of them are interesting. Let x1, x2, x3, and so on be independent, identically distributed random variables. And sometimes I've seen this in papers. Let me do the same here. So I'm going to add, I could call it x, but even this I've seen xi. So xi is like the mother of all these random variables. It's just you add one, and this is like your reference point. So if you want to talk about the expectation, so they are independent identity distributions. They all have the same expectation. But if I want to talk about that number, then I have to write like expectation of x1, y x1, or maybe x2 or x3. Then I have this xi, which plays no role in the story except for somehow getting rid of that dissonance. I could just work with x1 all the time as well. Okay, so this is the setting we have. And then we're going to form the average for Sn equal to the sum, n goes from 1 to big N of my xn's divided by n. And then, okay, so the weak law of large numbers says that Sn converges to the number expectation of these guys in probability. So, with our measure theoretic language, in measure. Now I'm going to do a proof, assuming that we have a finite variance. In the book, they strive for maximal, or at least as general as can be done, maximum generality, which is nice because you get statements which are as applicable as possible, but tends to somehow introduce a lot of details in the proof, which makes you kind of not see the core idea. So here I will do proofs where the core idea is easily visible, more easily visible, and with some additional assumptions. So we're going to do the proof, assuming that we have finite variance. Okay? So we start out by setting A to be equal to the expectation of psi, just to not have to write it all the time. Now, first of all, note that so epsilon square, epsilon of course is a fixed number. Well, yeah, no, that appears in the definition of convergence and probability that I sent out all back in the video you spoke up. So epsilon squared comes to probability of Sn minus A being bigger than epsilon. All right, so this is just a heads up. So clearly small n here should be a big N. And also there's an upcoming integral formula, which I'm going to mess up. But I'm going to fix it. So just, as I said, heads up. So it's all going to be all right in the end. Trust me. is of course equal to the probability for epsilon squared, and then I can put the square inside here to keep an observation. Of course, true. The point here is a bit that when I put the square here, I can get rid of the modulo we're dealing with real values, so you just get a parenthesis, and then later can turn this into an integral. So how can we turn this into an integral? Well, it depends on if we want to work on the left-hand side or the right-hand side of probability theory. So on one hand, this is equal to epsilon square integral over the set of omegas such that Sn minus A squared bigger than epsilon squared. So this is a set here. And then I have to integrate Sn omega minus A squared dilute. So all right, so here I'm just writing shit without thinking. Look, so there's two ways to fix this integral. Either you integrate over the characteristic function, or you move the epsilon square in front and keep the function as it is. But as written, it's just complete nonsense. And well, in the second case, if you keep the function, then it becomes an inequality, which is known as Chebyshev's inequality. So that's where I'm heading for. I'm just like, this is if we work on the left-hand side. But here I want to show that you can completely do this proof on the right-hand side of things. So this is often, like I've been saying, you often, many times in probability theory text, you never see this, like this fundament of it. So random variable is just something that generates a measure, and then you work on really work in this environment here instead. So I want to do that because it has certain benefits. It's certainly easier to see what's going on once you get used to their notation, right? So setting, I'm going to introduce a small function Sn of the vector x, which is just x sum xj or xn, and goes from 1 to big N, and then divided by big N. All right. This is the function now on Rn. And then we have the epsilon square times this probability, that guy, equal to epsilon squared. Now I integrate over the set of x such that Sn of x, I put this bar to indicate that these are really vectors now. So I integrate over this set here, Sn x minus a squared, and then I have the dx1 plus dxn. All right? Wait. All right, so now I spotted the error. God damn it, it's wrong in my paper, and I just rushed on without thinking. Okay, so I have to do this in 2 steps. All right, so okay, I integrate this over this set. But this then, of course, less than or equal to. Now, since this function is bigger than epsilon squared on the set I'm integrating, I'm just sticking that function there. Now we have the same set. So, in fact, if we call this set here AN, now what I'm interested in here is measuring AN, and then, okay, so then this set down here is AN, and now I do my function there, so I put Sn x minus A squared, and then my measure. It's a mess. It's so sorry. Ah, Jesus Christ. Well, I have this sorted out, and well, I mean, I have it sorted out, and I just put the details. Of how to express it most beautifully. Anyways, where are we going? But Jesus Christ, this is the quick part of the class. It's supposed to be, and we have the interesting part coming up. Okay, and from here on, it's just computation, yeah? So now you integrate over an. Actually, you can just forget this an and integrate over the full Rn. And then what is this? Well, it's this divided by n minus a outside, but if I put the minus a here, I'm summing up a n times and I'm dividing with n, so that disappears. So we have some xn minus a, n equals to 1 to big N, divided by n squared, dx1, okay, like this. But now, okay, so now I can expand this, but then by Fubini's theorem, this is an iterated integral because I have cross here products. So anytime I get a mixed term, I have to integrate xn against its probability measure. And then the other xm, let's say, to xm minus a and xn minus a meet, I integrate them separately, yeah, because this is what Fubini's theorem allows us to do. So you do iterated integrals, but then of course each integral becomes 0 because a is the expectation of the random variable xn. So when you integrate this variable against its measure, you just get a. So all of those terms disappear. And what you have here is basically just the sum of this, right? Because when xn meets itself, when I do the expansion of this, multiplying this, I think these are two big parentheses, and you multiply. So when xn meets itself, we get this integral, and all the other integrals, again, we use Fubini, they just integrate up to 1, right? So this is what we remain with. And now we recognize this as 1 over n squared times the variance of random variable xn. Okay, so here it's now again the sum. And they all have the same variance because they are identically distributed. So this becomes n times the variance. At the end of the day, I have variance of this psi, okay, divided by n. Okay, now this, as n goes to infinity, goes to 0. So epsilon is fixed, probability of an happening then goes to 0 as an goes to infinity. An is back here. So the set of points where x is mean of x is further away than x. 8. I have to look up what the name of this. My mind just went completely blank. This guy is called. The inequality I'm using here, this trivial one, but this is less than this. It is called not written here what it's called. Chebyshev, okay, Chebyshev's inequality. So this one less than that, that's Chebyshev's inequality. Good. So my point here, apart from telling you how to prove this, is to see that, okay, so mu was never really needed here. We could work really just on the right-hand side, but we're still working with integrals. But even that you can throw away because the integral of just any function, random variable, is the expectation of that random variable, right? So at some point, probability theory tend to just the integral disappears completely. And what we're using here, for example, Fubini's theorem and yada yada, that the mixed terms disappear, could be stated, for example, we have stuff like this proposition: if x1 and x2 are independent, then the expectation of x1 times x2, now I'm integrating a function times another, but if they're independent, then it's the same as integrating him and integrating him, right? Etc. It is just Fubini's theory, but now it looks like this. If you're not used to reading this, it looks totally confusing. But after a while, it's actually very, very convenient. So this is a proposition 10.1.10 is doing this in greater generality. Now with this, we can also prove things like we get here the variance of x1 plus x2 is equal to the variance of x1 plus the variance of x2. Now, why is that? Let's do a small proof so you just get the idea. So we have that the variance of x1 plus x2, that's equal to the expectation of x1 plus x2 minus the expectation of x1 plus x2 squared, right? Because this is what I need to integrate, so I can write the expectation there. Expectation, of course, is linear. So now I have expectation. So it's linear and I split it out. So I have expectation, sorry, I have this. And then I have 2 times the mixed term.
It should be a minus.
Right? So, yeah. And here, now I have the multiplication of 2 random variables which are independent. So I can get the expectation of this one separately, but that's just 0, and the other one is also 0, right? And therefore, I get the expectation of this square plus the expectation of that square, which is just variance of this plus variance of this. All right? So now, how can we redo this proof here without using one single integral?
The proof number 2 of weak law of large numbers.
So first of all, the expectation of Sn is equal to the expectation x1 plus xn divided by n, and then by linearity of the expectation, this is 1 over n times the expectation x1 plus expectation xn. And if these are independent, identically distributed, this is just equal to the expectation of psi, right? So, probability of Sn minus this number A bigger than epsilon equal to the probability of Sn minus expectation of Sn, because this is the same as this, which by definition is A, right? And then I can put the square here bigger than epsilon square. Now I use Chebyshev's inequality, which says that instead of this probability, I can just integrate this function here. Sorry, but for that, I need to put my epsilon square out here as well. Okay, so if I have that, then this is less than or equal to just integrating this function here, which then in probability language, here I'm integrating this guy square. So this is the variance of Sn, right? from integrating him alone. That's just the definition. Yeah, integrating him alone is the definition of the variance. And now I can use this statement here, iterated, so I have the variance of sum n goes from 1 to big N x n minus the expectation of x n if I want, divided by big N. Okay. Okay, that's another thing we could incorporate in this theorem, but of course, since there's a square here, we pull something out, we get a square on it, and then it goes from 1 to big N, the variance of x n, but they are all the same. So this is variance of psi divided by n. Exactly what I've written here. And if you go through step by step, what I actually did here is just a mirror calculation. This is for somebody who understands integration theory. This is for someone who's schooling, let's say, in probability theory, but both computations mean exactly the same thing. Right. That took longer than I hoped for. My girlfriend sometimes tells me. All right. So good. Now we move into the proof of the strong law of the large numbers. And this is the part of the lecture where it's beautiful. So stay tuned. I'm just gonna pause this thing, make sure it's safe so the stupid computer doesn't shut down on me again. Lose the material, and then I'll be back.
All right. Let's do this. I hope I can manage. What's case I got it halfway through, but all right. So the statement is as follows: independent, identity distributed random variables. So with a strong law of large numbers, Sn equal to the sum of xn, the average, rather, and the statement is that the limit Sn omega is equal to the expectation of psi, which or x1 or what you want.
Almost surely. So the set of omega such that this holds is a set of measure 1. And then we do a proof, assuming that the variation of psi is less than infinity. This it simplifies a lot. So basically, to help you, I mean, you have to go and read the book here at some point, right? And I'm going to help you understand what's going on in the book. And usually to understand the proof, you have to go backwards. You have to understand like what's the final idea. And then you kind of go up like, okay, that's why they need this piece. That's why they need this piece. That's why they need this piece. And that's a bit how I will explain it here also. So the theorem we're proving is 10.2.5. And it has some statements before the proof, which comes on page 323. And here it starts with them introducing some variable yi, which makes this proof impossible to read. The point of this yi is that don't want to assume that x has finite variation. Just assume that the expectation exists. And then, so if x doesn't have finite variation, then the y corresponding to the x I doesn't have finite, and the yi will have finite variation, and then they work with those instead and manage to get around this fact, right? But if we throw that away, the yi and the xi can be taken as the same, and we get a much simpler proof. Okay, sorry, the focus was out of focus. Right, so even if we have a bunch of sequence, a sequence of numbers, so x1, x2, dot, 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 dot. So if this is, let's say, a realization of this, it's hard to work with the average because the denominator keeps changing. So one of the really beautiful ideas of this proof, there are many, is, okay, let's skip that and introduce instead the following. We're going to introduce Tn as the sum, and go from 1 to big N, xn divided by n, right? So small n instead of big N. So we can think of this, let's do a graph here. So here's my big N, here's 1, and then these are the Tn weights.
That's small n, Tn weight.
Whereas this is the Sn weights, right? Sn weights, I hope you can read that. So, in a way, the weights I have for my sum here is like a plateau sitting under the weights of the corresponding Tn. Now, this is easy to paint, but one way of formally somehow writing this down, which in itself requires some thought. So Sn is equal to Tn minus sum why? Because in this sum, what's the kth summand? So if we take here some point K, so in the Sn, we just have xk divided by n, right? For the Tn, we have xk divided by k. And here, so T1 just sums up x1 divides with 1. T2 sums up x1 again, dividing with 1, and then x2 divided by 2. Point is that x2 comes first in T2, right? Same x3 appears first time in T3, and so on. So if you just count how many times these factors show up here, you realize that here I have a 1 over n, then an n minus k divided by k, right? So the divided by k comes from that this division by k sits in each factor in the tk. Yeah, so these are the weights here. You do 1 over k. And then how many times does it show up? Well, if k is equal to 1, then you get the n minus 1 there, right? If k is equal to 2, then it appears again n minus 1 time, but the first time it's not there because it's not in T1, so I get n minus 2, and so on, right? So we can understand this. Now, if you look at this, so this 1 over n cancels that 1 over n, and there's a 1 over k left. And here I get a minus 1 over n. So I have a 1 over k here, minus a 1 over k there, minus 1 over n. So that's a minus minus. That's a 1 over n here. So, right? Already simple formula, but beautiful in its own way. Now, here's the really beautiful observation. Okay, so here I have like something I can work with. The only thing that moves with n is this, right? Not the weights, as in here. Now, if Tn converges to something, then here I have an average of something that converges, so this thing is going to converge to the same thing. So just the fact that Tn converges to something means that this converges to the same thing, and then the difference converges to 0, which is what we want. Yes? So, okay. Why do we want this to be 0? Because at some point we will say, let's do the proof, assuming the expectation is 0. Yeah. So if you have the proof for when the expectation is 0, then it's just some linear blah, blah, blah to get the general statement. So assuming this and expectation of psi equals to 0. So this is not a major restriction. So now we just have to prove that Tn converges to something in order to see that the Sn converges to 0. Okay, so then the strong law of large numbers will follow immediately if we prove the following statements. So proposition that Tn equal to some little n goes from 1 to big N, 1 over n xn, then limit Tn omega n goes to infinity exists almost surely, right? So I'm not saying this converges to 0, I'm just saying it converges to something because then Sn will converge to 0. Thanks to that formula we had up there. Proof. So this piece, what I'm doing here is basically all pieces of the last part, like the proof, the actual proof of 10 to 5, but I've thrown away all this, the complications involving y. Yeah, well, okay. So what I just told you, that was basically the main idea in the proof of the strong law of large numbers. Now I'm in proposition 10 to 7, which is a pre-proposition. Basically, I'm just repeating that proof, which is super nice in its own way. Right, all right. So x and here are independent, identity distributed random variables. Just as before, right? And with expectation 0 and finite variance. So by independence, we have the variance of our Tn is the expectation 1 over n xn, and we go from 1 to big N, right? Because the expectation of each guy, sorry, with a square, right? Because the expectation of each xn is 0. And now they are independent, so just like we played around in the weak law of large numbers, this is nothing but sum n goes from 1 to big N, 1 over n squared out here, and then I get the variance of xn. Well, I get the expectation of xn squared, which is the variance of xn. But this is all the same number because they are identical. So I have constant times that sum, which we know is convergent, right? 1 over n squared converges, so this is less than infinity. Here it gets d, okay? Pay attention. For a fixed value n, an integer that's going to go to infinity at some point, I pick another integer nn, such that sum n goes from nm up to infinity, 1 over n squared, variance of this guy side, is less than or equal to something which is extremely super small. I can of course choose what I want here. I choose 1 divided by 2 to the power of 3m. Of course, because this is a convergent. I mean, it's n goes to infinity, this is convergent, so then I can choose the k as small as I want. Okay, now I'm going to introduce a set. So let an k, okay, equal to the set of omega such that sum n goes from nn up to k xn divided by n modulus is bigger than 1 divided by 2 to the power of m. Okay, so this depends on my k. Now, Chebyshev stated in probabilistic terms would say that the probability of this set A and K is less than or equal to integrating, well, this thing square, and then I have to multiply with this constant here, right? So, well, 1 divided with the constant. So multiplying here with this constant squared, then I get less than or equal to the integral of this thing squared. That's Chebyshev's inequality. So if instead of multiplying with this on this side, I divide with it here, I get 2 to the power of 2m. And then the integral, but now we agree to write expectation instead of integral. Right, and they're all independent. So this is less than or equal to 2 to the power of 2n. Well, just as here above, we see that this is some n goes from n, well, to infinity, because I don't need to stop at k, and then the variance side 1 over n squared. Same computation as above, just not stopping at k, I go higher, of course I get something bigger. And this then in turn is less than or equal to this tail here was chosen with less than or equal to 1 over 2 to the power of 3m. So I get 1 over 2 to the power of m. So this is of course the whole point. This set is small. Unfortunately, okay, this is good, but this is not good enough, because what we will need, so what am I aiming for here? Of course, we want this thing here for evaluated at some omega to converge. Then I want the tail to be small. So here I'm kind of looking at omegas where the tail is not small. Okay, so think basically places where things screw up. But whether the tail is small or not for a fixed k is not so interesting. You want to know that the tail is small for all k's. So what we're going to do is we're going to introduce the set an, which is equal to the set of all omega, such that the maximum over k bigger than or equal to nm modulo sum right? But now I cannot really use Chebyshev's inequality any longer, because Chebyshev's inequality, I'm forced to work with a fixed function here, right? But now I have this max, I have this whole jumble bumble of lots of functions. So instead of Chebyshev, there is an improvement to Chebyshev, which is way more clever, by Kolmogorov. And this is, well, Kolmogorov's inequality is called as 10-6 in the book, which basically in this setting says that the probability of AM happening is less than or equal to, well, the same guy there, so 2 to the 2m. So, but yeah, here, and then the expectation of this, but I can let k go to infinity. So basically, the application, what we get out of that theory here is what we wanted, same as over there. But don't be fooled and think that, yeah, this is just something simple. This is in itself a very nice statement. Oh, the n should, of course, have a square in it. Sorry. Okay, and then, well, look at that. Now I don't even have to write. This is less than or equal to this, and that's what we want, thanks to this Kolmogorov inequality. I will explain Kolmogorov's inequality after I'm done with the proof, so you kind of see where this whole argument is going and why Kolmogorov's inequality is needed. So we have these sets AM where things are not behaving very well, which means, but they are small in measure, right? So the probability of this set is a very small number. So outside of those AM, things are behaving very well, yes? So what we have is that the mu of AM is less than or equal to 1 over 2 to the power of m, so a small set. Well, now I switch notation, probability of AM, mu of AM, same shit. And outside, we have, if I'm looking at TL minus TK, like some omega, is equal to, and now I can do different silly things, so T or L minus T and M minus TK minus T and M. Of course, evaluate that omega again. I'm not writing that out this time. So now, if L and K are bigger than NM, then this is less than 1 over 2 to the M. Right? Because this difference of the TK and the TL is one of these tails, right? So the TK and the TNM it becomes exactly this, well, actually with N plus 1 here, but it doesn't matter. Yeah, so technically then it should be NN minus 1 here. But anyway, so I know that this shit is smaller than 1 over 2 to the power of M outside of my AM, right? So if I'm outside of AM, this is less than 3 times 1 over 2 to the power of M. Okay, and that happens for all L and K bigger than NM. Now, if I let M free, so now consider, so if I take the union of all the AMs, starting at 1, going up to infinity, then I'm outside, well, yeah, if omega is outside of all of those guys, then if I pick some epsilon, you can pick M, but that this is less than your epsilon, and that M gives you your NM, such that for L and K bigger, this difference here is smaller than your epsilon. Meaning, outside here, T A, let's call it omega, A goes from 1 to infinity, is a Cauchy sequence. And hence it converges, right? Which is what we wanted to prove. We said that if the Tn converges, the SMs go to 0, and that's what we wanted. Okay, so now what's the measure here? The measure of this union of the ANs is less than or equal to sum, and goes from 1 to infinity, 1 over 2 to the power of m. So that's less than 1. Well, that could actually be the whole space, right? Because we're dealing with a probability measure. But consider now omega outside of this thing. I start higher up. You know, whether this is Cauchy or not doesn't depend at all on what happens in the beginning. So no matter how late I start, I still get that it's a Cauchy sequence, and hence it's convergent. And now the measure of that thing can be made as small as I want. But I won't measure 0. But basically, you realize now that as long as you're outside any one of these guys for some m, you're fine. This omega will produce Cauchy sequence. So the interesting thing now is the set where things can screw up is only the intersection of all of these guys, and you recognize him, right? And well, the measure of these guys gets smaller and smaller, goes to 0. The measure of this thing is 0. So for almost every point omega, i.e. every point outside of this thing here, this is a Cauchy sequence, and therefore the Sn of omega, if you make these big letters, will converge to 0, because these guys, this converges to something, and then that thing converges to the same. Really, really fantastic mathematics. So it remains to understand Kolmogorov's inequality, which was this one here, right? And that I will do in a separate video. I'm gonna reformulate it a bit so it looks, I mean, here I wrote it how we needed it in the application, but instead of having something starting at nm and going to some k, we can start at 1, and instead of having this particular number, we're just going to have some epsilons. It really looks like the Chebyshev inequality. And then, so I'll first state it like that, and then I'll explain you the, well, it's getting a bit saturated here with me claiming things are beautiful and so on, but this proof is also really, really nice. So stay tuned. I'm going to erase the blackboard and be right with you. Commercial break. All right, so let's see if we can do this before these people show up. Where's the pen? Kolmogorov's inequality. So we have x1, x2, so on, independent, identically distributed random variables as always. Now with expectation, okay, let's start with psi. Psi equals to 0, okay. But with expectation 0, I could have just written it. Anyways, and then with no weights or anything like we had in the previous proof, just you're only summing them up. Let me use the notation of the proof. So S little n now would be the sum over I of these xi's, okay? And then Chebyshev inequality would say that the probability of modulus Si bigger than epsilon for some epsilon. Now, if I multiply this with epsilon squared, this is an integral over some characteristics over some set, and on that set, this function is bigger than epsilon squared, so I just can integrate the function square instead. And if I integrate this square, they're all independent, right? So I get the expectation of this sum square, but yeah, they're independent, so I get the expectation of each x1 square, xi square separately, and then I going from 1 to little n. Okay, so this is what Chebyshev would have said. If you want, you can put some omega here, okay? Now, what Kolmogorov says is that we can add here the max, 1 less than I less than n. Okay? So how we're gonna do this, okay, and then, right, all right, so if we want, this is the same, of course, as the variance of xi, so it's different ways of expressing the same things. Now it looks like Chebyshev, but with this max sitting here. So if the max is bigger than epsilon, then there is some Si for which is bigger than epsilon, and then there is a first Si for which it is bigger than epsilon, right? Let's put Ai to be equal to the set of points omega such that S j is less than epsilon for all j 1 dot 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 I minus 1 and Si bigger than epsilon, okay? So somehow we can think of this as here's my set omega, and then I have an A1, A2, they are both disjoint, A3, and the set I'm interested in estimating here is the union of those guys. Now, clearly, I can do Chebyshev on each one of them and get that the probability of AI is less than or equal to, let's say, 1 over epsilon squared, putting this one here. And then, well, the expectation of SI squared, let's put it like that. Okay, so this we know now just becomes the sum up to I. Yeah, because they are independent. But don't make the mistake of thinking that we can just add this up and get this one. So here we have now with our new notation union AI, I goes from 1 to n, right? So if I estimate this one with this, which in turn is less than that, right? Then I get that for every I, but then if I want to sum these off there, this joint, then I get an n here in front. And that's clearly not what I want. So the beauty of this theory is that this estimate here, well, you can go from here to here without increasing this constant. Well, what you have to do is you have, instead of I, you put an n here. Okay? But, so how can I here in this integral, if I swap from Si to Sn, note that Si, of course, is equal to, well, Sn is equal to Si plus the remaining term, so Sn minus Si, if you want. But that does not mean, so somehow we think of this, okay, you have more terms here, so it's bigger. It's not, because there's no modulus here. So if I, instead of Si, for each point omega in AI, this has some value. The value of Sn can clearly be smaller there, because I'm adding this piece, which might be negative, or which will be negative for a lot of points, right? So there's no reason for me to, well, at least intuitively, there's no way of just forgetting my I and putting an n here instead. But it can be done. So let us now do the integral over our AI of Sn squared, okay? Against mu, here in the book they have P, because now apparently mu is out, they call it P instead. Fair enough. I'm still calling it mu. And now I'm using this identity. So this we can think of as characteristic function of AI, and then Si plus Sn minus Si squared. And here is where the thing gets really beautiful. So, yeah, so we expand this, right? We get 4 terms, but the middle term, we can think of it as characteristic function of AI times him multiplied with this guy, right? Now, this one is made up of x I plus 1 up to xn. This sum is made of x1 up to xi, and that set here, look at the definition, also only involves xi from 1 up to xj from 1 up to I minus 1. So this set here is produced, we have like, okay, this goes to xi minus 1, and then it continues xi because xn. So the latter piece is produced with this, sorry, xi and xi plus 1. The latter piece is produced with this, the former piece is produced with this, and now we have this curious, beautiful proposition 10.1.7, which I told you it's hard to read, but pay attention because we're going to use it a lot, which tells you basically that anytime you have random variables that are independent and you do something with one group here and another group here, whatever you do, basically the new things are going to be independent as well. So, armed with that, we see that, yes, let's do it like this. Instead of integral, I'm writing expectation, okay? And then, of course, I have the expectation.
Characteristic function AI SI squared plus SN squared, and then plus characteristic function AI SI times SN minus SI, right?
And now this is expectation of that, plus that, plus this. And here, this one is independent of this. So I get the expectation of this shit here, which I don't know what it is. So this is basically one of the exercises we did in the previous lecture. But here, this one has expectation 0 and this one has expectation 0. So the expectation of this thing here is equal to 0. And that's why I can throw this guy away. And at the end of the day here, I have equality. Let's go, well, expectation of this plus this. All right, so final correction for this pathetic lecture. So the Sn there, so the Si squared, and then you have Sn squared. Clearly, it's supposed to be Sn minus Si. I was rushing because I knew there was people coming in. So, anyways, then it doesn't matter because whatever I'm gonna say, the conclusion where I get to in the end is correct. So let's go back to integrals. Sn squared over AI plus Si squared the mu, and now this is a positive function and this is a positive function which is added to that guy, so this is bigger than or equal to integral AI Si squared the mu, right? And now, armed with this, let's do this here. So what we're interested in is, okay, we were interested in epsilon squared probability union the AI. Which then I write it as a sum. So they're disjoint, right? And now I'm using, well, this in combination with this, so this here is the expectation of that, right? So I get epsilon squared integral, well, and here's my sum, then AI SI, but from this computation here, I know it's less than corresponding to Sn squared. Right, and now I have one function, not different function, and I'm integrating over disjoint sets here. So this is less than or equal to, well, less than or equal to epsilon squared integral Sn squared the mu. No, okay, so here, right, I divide with epsilon, the epsilon squared is here, and then I get this. Right, so now this is the variance of the Sn to the sum, I go from 1 to n, it's then the variance of my x. Okay, so what I want to do. Very nice. Have a nice summer, or if you're watching this a few years down the road, have a nice, well, I don't know why should I end this with have a nice. Okay, thank you for watching. Goodbye.